from last time we saw that the critical point was inside of the boundary. So it looks like this red dot here, the point 2, 3, is a possible candidate for a global or absolute max or min. But we also have to wonder if there might exist a maximum or a minimum within the boundaries. And so what we need to do is we need to check the boundaries. Maybe I should have done this in another color. So let's check the boundaries. And it looks like there are 4 sides to this. And so those are 4 different things we want to consider. So let us first consider this boundary here. Let's call this boundary 1. And that boundary is when y is equal to 0. From 0 to 4 for the x values. So what we want to do is we want to put that into the function f of x comma 0, because y is equal to 0, into the original function. And we have 4x. We got 0. We have minus x squared, 0 plus 4. So now you just have a function of x and you can treat this as if it was just like a regular problem in Calc 1. So let's call this g sub 1 with a 1, the same 1 that we're using for the name of the boundary of x is equal to 4x minus x squared plus 4. And then now, since this is just a function of one variable, we could take the derivative of this by just calling it prime. 4 minus 2x. And then we can set this equal to 0 and find the critical points. So x is equal to what? 2. So x is equal to 2, y is equal to 0. It's not a critical point for the function as a whole, but it's a critical point that happens in the boundary. So 2 comma 0 is going to be another point that we want to check. So we're going to check that point. We also need to check the endpoints, but I'll focus on the endpoints a little bit later on. All right, so that's 1. Let's call this boundary 2, and let's check boundary 2. Boundary 2 is a fixed x value. X is equal to 4 when y goes from 0 to 5. So we'll take our function again and put 4 in for x. And so now it'll end up being a function of y. So f of 4y, I'll call that g sub 2 of y in a minute. So I want to put 4 in for x. I got 16 plus 6y minus 16, right? 4 squared, yep. minus y squared plus 4. And then the 16s go away, and I'm going to call this G2 of y. So now I just have a function of y, one variable. And that is just 6y minus y squared plus 4. So the same deal, I will take the derivative, set equal to 0 to find the critical points. And then I'm going to get y is equal to 3. So now I have another point, x is equal to 4, y is equal to 3, that I have to check. All right. So it gets a little tedious, but if we just walk through this, I think we might see some patterns. I don't know. The third side is when y is equal to 5, x is between 0 and 4. So f of x comma 5 will now just be a function of x. So we'll put 5 in for y, so I get 4x plus 6 times 5 is 30 minus x squared plus y 5 squared, that's 25, plus 4. So it looks like it's just going to end up, I'll call this g sub 3 of x, a function of only one variable, so I can just do the prime. We got 4x minus x squared plus 1, no, double, plus 59. So I want to take the derivative of this to find critical points. And then I'm going to get x is equal to 2 again. So my other point over here is 2 comma 5. And then finally, the last one is when x is equal to 0 for the values of y from 0 to 5. So f of 0 comma y will give us 0 plus 6y minus 0 minus y squared plus 4. And then let's call this g sub 4 of y's function of y. Let's take the derivative already. 6 minus 2y, which is again going to give us a 3 when we set it equal to 0, so we get our last point. 0 comma 3. So far we have 5 points to check. Should we check anything else? What? Yeah, I kind of mentioned this earlier. We should also check the corners. So now we have 9 points to check. Boy, really nice if I had a computer to do this. So I can just change those values. Okay. So these are the endpoints, corner points that we should also check at 0, 0, 4, 0, 4, 5, and 0, 5. All right, well, let's check them. Let's start with our critical point, 2, 3. So f of 2, 3. Maybe we should have started with something else. Anyways, we put 2 for x and 3 for y. What do we get? We get an 8 plus, oh, this is too much for me. Probably don't need Mathematica to do this, but it's too much. I just can't take it anymore. So my function is f is a function of x and y. It's 4x plus 6y minus x squared minus y squared plus 4. All right, so what are my points? I'm first looking at f of 3, f of 2, 3. I got 17. I need to figure out my f of, what's my first one, 2, 0. Let's just do a bunch of them. F of 2, 0, f of 4, 3, f of 2, 5, and f of 0, 3. So 8, 13, 13, and 13. So first I had 17. So I had 17. And then instead of writing all that stuff down, I'm just going to say this would give me, what was it? 8. And this gave me 13. This is 13. And this is 13. So right now I have a high of 7 and a low of 8. But again, we need to check the endpoints. So let's check the endpoints. 0, 0, 4, 0, etc. F of 0, 0, F of 4, 0, F of 4, 5, F of 0, 5. So 4, 4, 9, 9. Four, 4, 9, 9. Oops. Which one did I do first? 0, 0. Crap. So 0, 0 gave me 4. This gave me 4. This gave me 9. And this gave me 9. All right, got it. So the absolute maximum value looks like it's 17. And we got that absolute maximum value from the critical point. So remember, when they're looking for the value, they're looking for the output value, not the point. They might look for the point, in which case you would say 2, 3, 17, but in this case they're just looking for the absolute value. The absolute minimum value looks like it happens twice in this closed set, and that's 4. And when you attain the minimum value, absolute minimum value at 0, 0 and at 4, 0. Okay? Any questions? No. Okay, there are no questions. We can move on, yeah?
Is there a shorter way of doing this?
Unfortunately, because the boundary is made up of 4 separate pieces, it's a little bit more difficult. Sometimes you get a boundary that's a circle, and so that's just one equation that you can substitute somewhere to the function, and then that would be nicer and easier. But in this case, I think some of your homework problems ask you to check it on a boundary that's a triangle, so that's 3 sides instead of 4. But then you have to find the equation of the line, you know, of the triangles of those 3 lines. Here the lines were easy. The lines were 0, x is equal to 4, y is equal to 5. They're just, you know, horizontal or vertical lines. With a triangle, inevitably one of them is going to be a non-vertical or horizontal line, so you'll have to find that equation using your algebra skills and all. Okay? Any questions? I didn't check if you could see this in a, oh, I suppose we have this Mathematica up already. Let's check it using Mathematica. So our function is f of x, y, and here I get to put boundaries for the x and the y. So the x goes from 0 to 4, and then the y goes from 0 to 5. And if I graph it, the thing about Mathematica, when it graphs things, it kind of graphs things disproportionate, so sometimes I need to change my ratios. And this is a little more to scale, and then we can kind of see those 2 values that are all the way down in the bottom and the 1 value in the middle up on top. So I think if we take a good look at this, where's my x? Well, let's just take a picture of it and then take a look at it.
Well, we know that the x is the bottom axis. That's what you look at.
It's on the x.
Yeah.
So this is our x right here, and our y. So the two low points happen here, and this has a height. This is 5 over here, so this has a height of 4. And the maximum values, 15, 16, 17, is happening pretty much in the middle of this, 2, 3. And that gives our maximum value. So those other values that we saw had a value of 8 or something. Is that 8? It looks like it's 9. 5, 6, 7, 8, 9. Was it 9? It was 9, yeah. It was 9. So these have a value of 9. And then we saw a couple of 13s, right? So they're happening over here. And then on the other side that we can't see, this has a value of 13. So that's how it looks like from our two-dimensional picture where we couldn't see the surface itself to now if we actually look at the surface and see how those points correspond with the points that we have. I think it becomes a little clearer what it is we were looking at. You know, instead of just looking at a flat plane and a bunch of dots and some numbers that I was putting out here, well, now you can actually see how those numbers are related in a three-dimensional picture. Okay. All right. So, any questions? Yeah.
Can you say again that step to find the maximum total find the critical point?
Yeah, so just break down. Maybe I should type this one out. Let me move this over here for a second, and let's do a little summary. So find critical points. So your critical points, remember, because this is a function of two variables, your critical points depend on the two partial derivatives being set equal to 0. So that in itself is a little bit of a challenge. Now, we don't have to do the first or the second derivative test for this because we're just going to check and compare this with other possible candidates for absolute max and mins. So we can do this later. After we find the critical points, how should we put it? Find the critical points in the boundary. Now the boundary, there could just be, like I said, if it's a circle, then that's just one boundary that we're looking at. But if it's pieces, line pieces or curved pieces put together, then we have to take into account the different boundaries that we have to consider. So in our example, we had 4 boundaries that we need to look at, 4 lines that made up our boundary. And then also find anything, any endpoints. So by endpoints, I mean like vertices. In that case, where we had 4 lines, you had to look at all the points that are connecting those 4 lines. So usually connecting multiple boundaries, if you had multiple boundaries. So you have critical points. In our case, we only had one. We found critical points in the boundaries. In each boundary, we found one critical point, so we had 4 critical points for those boundaries. And then we had 4 points that connected those boundaries as our endpoints. So we had a total of 9 points to check. So once you have all these possible places where you have your max and min, you need to check them. And if we put that into the original function, we're going to come up with, hopefully, one of them would be the largest value, the other one would be the smallest value. In our case, we found 2 absolute minimums, but the value itself is the same. So here's your summary. I hope that makes sense based on what we did. Maybe I should put this in another page. Okay. All right, let's take a look at our next section, which is still dealing with max and mins, and actually, more specifically, is dealing with maximums and minimums and a constraint. So if you remember back in Calc 1, when you start doing optimization, you had problems where you're trying to maximize something given a particular constraint. You're trying to maximize, I don't know, the area of a fence that you're going to try to enclose, but you only had 60 meters of fencing to use. So that's kind of like your constraint. So back in Calc 1, I'll use that fence example. That's the easiest one.
I messed up on we had done our text right now.
Maximize area given fixed fencing. Of P meters or something. So you're trying to maximize the area, and you have a fixed perimeter, P. And so you need 2 things. You need a function to maximize, in this case, it's the area function. And then you need a constraint. And the constraint was the perimeter. So the perimeter was 2x plus 2y, and that's equal to some fixed value p. So it turns out it's that fixed value that we want to deal with. This is kind of written down already, like it's should be in Calc 3, right? I wrote my a function as a function of two variables, and then I have my constraint that has two variables. Well, in Calculus 1, we would use our constraint to solve for x or y and then plug it back into a, and then now you just have a function of one variable and then just solve for that. But let's take a look at this, because this looks kind of interesting. Let's bring this very same problem into Calc 3, and I want to graph it using the computer, and so I might be interested in changing the p into an actual number, like 10. So let's change this to 10, because I can't graph p. So this looks like functions of two variables. So the question is, how can we relate these two functions? We have a as our first function, and then we have this thing, which I guess we can call our second function. Actually, let me call this f. Can I call this f? Yes, thanks. As if I needed your permission. And so maybe we can call the other one g, but the g looks like it's equal to something in particular here. You know what we should have done? We should have solved for this using Calc 1. You want to solve for it using Calc 1? You remember? Anybody tutoring Calc 1? By the way, I always throw this plug. If you guys are taking these calculus courses, you should be tutoring algebra, from algebra to pre-calculus to trig to the other calculus that you've already done, just so you can retain some of that idea. Because you know, you guys took Calc 1, what, 2 semesters ago, 3 semesters ago, 5 semesters ago? So if you guys were tutoring it, this would be kind of semi-fresh in your heads. But if you haven't seen it since then, the last time you've seen this was 3 years ago, and then that's... Was it 3 years ago? 2 years ago? Last spring. A year ago. That's still a long time from now. So I encourage you to tutor. All right. So back to this problem. I have a function that I'm trying to maximize, and then I have this thing that is kind of forced to equal a constant. What do you think of when a function of several variables is equal to a constant? Okay, but let's think about this. You're right, it is a line in this case. But let's think about this as a function of two variables, and the function of two variables is equal to a constant. What do you think about when you let a function of more than one variable equal to a constant? Anybody? Throw some words out there. 3D graph. So if you let it equal a constant, Rick said that this is a line, and I agree with him. This is a line. So a level set. In this case, it's a curve, but it's a level set. Okay? So if you let this equal a constant, you have a level set. So I have a function here that could be represented as a function in 3 variables. And then I have this function here, which is a level set, a fixed level set. So, now what? So now I might be interested in trying to figure out what the relationship is between this 3D function and this 2D function. Why don't we bring this 3D down to 2D? So wait, before we do that, what did I just say? This is a level set? Or I guess Lauren said it. So this is a level curve, and this isn't right now in 3D, which is at the moment not very helpful, but this is a function. So why don't we consider this, bring this down to the same level as the level set. So why don't we consider levels curves for F. Okay, so let's see. I guess I have Mathematica up already, so let me continue working on Mathematica. We're considering the level curves for F. This is not the same F function, so let's redefine F. So I want contour plots. Let me spell contour wrong. Contour. And I need parameters. I need to get my x. I don't want negative numbers here, so I'm not going to start with a negative number. So I'll go for 0. And then my fencing is 10, so I don't need to go past 10. I can go up to 10 maybe. Let's go up to 10. So when I do a contour plot, I get something that looks like this. It's shaded for me. It even has, if I move my mouse around, I get the contour, so I get the heights of these things as well. Okay, that's interesting. Now that I brought that down to that level, let's graph this graph. Let's take the contour plot for that one as well. So let's take the contour plot of 2x. I suppose I should simplify this, but let's keep it like that. 2x, 2y. That's your function. And let's also go from x is negative 0 to 10. And y goes from 0 to 10. And this time, I don't want all the different contours. I want one specific contour. So let me specify a specific contour. And I want the contour when x is equal to 10. No, I don't want 10 contours. I want one is equal to 10. Is this going to work? Plot style? I can't use plot style. I can't use style. I don't want the shading. Can I just say shading? Shade? Ah, crap. I don't have the commands off the top of my head. Contour. Shading. False. There it goes. All right, where's the other one? The other one's there, so let's show both of them. I can't see the other one. Damn it. It's all the way over here. All right, well, we'll just have to take that. So I'm a little rusty with my Mathematica. What we have here is this level curve, this one level curve over here. And then we have a bunch of level curves for this. And the one that we actually want is not here, so I'm going to add another level curve for F. And what happens is that there's this special point, X and Y point, where we attain the max and min. And had we solved for this using our Calculus 1, we would have gotten this point. And it looks like that point should be, I don't know, whatever that point is. Should we solve for this using Calc 1? Do you remember how to solve for this? That's 2.5. So the way to solve for this is that you, back in Calculus 1, since we can only deal with one variable, we would solve for one of these variables. And then we would take that and plug it into your a function so that you have x and then y, which is 5 minus x. And so that would be x times 5 minus x. And then now you have a function of only one variable, x. And let's FOIL it out. There's 5x minus x squared. So from here, you take the derivative, set it equal to 0, and do all that kind of stuff. So f prime of x is equal to 5 minus 2x. So x is equal to 5 halves. So that's your critical point. So when x is equal to 5 halves, you put it back to solve for y. Y is also equal to 5 halves. So you have the same x and y value. And what happens is that that's the point 5 halves, comma 5 halves over here. So my point in doing this graph is to show you that there's a relationship when you're trying to maximize something and you have a function that you're trying to maximize. You have a function that you're trying to maximize and a constraint. You could take a look at the level curves for that function and then take a look at the constraint as itself a level curve. And then that place where they meet and touch, not that they intersect, because there's more graphs over here. There's other graphs over here that intersect that line. But it's this one place where they intersect, how do they call it? where they kiss. That's what mathematicians call it. Where they're tangent to each other. Have you heard of that? Where they kiss? They have kissing spheres and stuff like that. Yeah. Romantic. Sure. Yeah. Censor. It's all kinds of stuff going through my head now that I have to censor. Anyways, so back to this idea that you have kissing curves. When two curves kiss like that, what can you say about these two curves that just meet like this? They're tangent. The tangent lines are the same, right? Furthermore, if the tangent lines are the same, my question is kind of going to be extended. These curves are coming from level curves or level sets, right? And you're saying that I want to find points on these level curves that are tangent to each other, that have the same tangent line. Now, finding the tangent line isn't the easiest thing. What is easy in terms of finding something from a function that's related to a level curve? That's a long, complicated question, and I want one specific answer. So the answer is a gradient. What's the gradient? What is one property of the gradient? It's perpendicular to the level curve. If it's perpendicular to the level curve, that means the gradient is perpendicular to the tangent line, right? So if it's perpendicular to the tangent line, that means the gradient for the function that you're trying to maximize and the gradient for the constraint, irrespective of not counting whatever this number is, it doesn't matter what that number is, because we're not going to care about that. Well, we will later on. But in terms of just looking at this, the gradient for f and the gradient for our constraint function has to be what? Could be the same. If it was the same, it would be great. But at least what? About the same. So the word I was looking for was collinear. Parallel. Or how would you say, what is another feature of two vectors being parallel to each other? Same direction, or it could be totally opposite, but mathematically, what can we write about these two vectors? No. I mean, what? Yeah, the same normal vector, same slope, same direction or opposite direction, same or opposite. What makes it go opposite? A negative sign would make it go opposite, right? What if they were going in the same direction, but one of them is longer than the other? They're what? Scalar. So they're a scalar multiple of each other. That's what I was trying to get at. Well, at least that's what I was trying to get you to say. Thanks, Moises. Now, if it's a scalar multiple of each other, then we can write this equation. The gradient of f is equal to what? Lambda. Have you guys seen this Greek letter lambda? Lambda. So lambda is a scalar. And what we're saying is that the gradient of f is a scalar multiple of a gradient of g. So if we can get this going, then we have this particular relationship. Then it means those level curves must be kissing. Now, we also want to make sure that we're only choosing one level curve for your constraint. And so somewhere along the line, we'll need to use that information as a level curve. So, you know what lambda stands for? Why did they use lambda instead of alpha or something else? Alpha could be a scalar. I could have chosen C for that matter. So this is called the method of Lagrange multipliers. So Lagrange multipliers, and that's where lambda comes from. That's where the L comes from. So Lagrange multipliers is a technique that you can use, if you're trying to maximize or minimize. Let's say optimize, because optimize stands for both. And f could be a function in 2 or 3 variables. Hell, it could be a function in one. Now, let's stick with 2 or 3 variables. So f can be a function of 2 or 3 or even more variables. But in most of the cases we'll just be staying with 2 variables. We're optimizing f given constraint g and equal to a constant. And again, g would have the same number of variables as f. So let's do that example where we're going from R2 to R, our simpler case, in the case that we kind of just did. So if f is a function of that goes from R2 to R, then what we want to do Lagrange multipliers is we need to solve for the gradient of f of xy is equal to lambda times the gradient of g of xy. Now, from this, how many equations will we have? This one equation is going to generate more than one equation. How many equations will we really have? No. 2. What are the 2 equations? The 2 equations is the partial of f with respect to x. I'm sorry. I'm going to use the other notation. F sub x. That's the first component of this, right? Is equal to, now this g is going to be the partial of g with respect to x. And then the lambda is going to get distributed to the first component and the second component. So this is one equation, and then the partial with respect to y is your other equation. So I have 2 equations. How many unknowns do I have? No, you went too fast.
3.
3 unknowns. Good job, Mimi.
Thank you.
So the x is one unknown. The y is your other unknown. What's your third unknown? Lambda, because we don't know what lambda is. So we have three unknowns. So we're going to solve for three unknowns. Wait, we only have two equations. So we need a third equation. Our third equation is going to be our constraint. So k looks like it's another unknown, but it's actually a constant given. Given constant k, and now you have those other two variables, x and y, the same x and y that you're going to be solving for. So we have three equations now and three unknowns, and we should be able to do this. We should be. It's usually hard. So the concept is easy, and this is really all there is to Lagrange multipliers in terms of laying it all out. And when we do some simple examples, maybe those simple examples will be easy, but sometimes the solving for x, y, and z can get kind of weird and hairy, and you need special tricks and techniques that you may have learned at one time and forgotten, or you may have not learned yet. And so that's where the tricky part comes in. So let's do an example, and more specifically, let's do our example that we were just looking at. We have our f of xy is equal to xy. This is our area. And our g of xy is equal to 2x plus 2y is equal to 10. So let's see if we can solve for, our answer is 2.5 comma 2.5, right? So that's our x and y value answers. So let's see if we can get that. Let's go through this process. We need the gradient of f. That is going to be derivative with respect to x is going to be y. Derivative with respect to y is going to be x. And then the gradient of g is going to be 2 comma 2. So it just turns out to be constant. And that kind of makes sense if we look at the picture. Remember, Rick said that this was a line, and the gradient is perpendicular to the line. So if it's a line, then the gradient's not going to change as you move up and down the line. So the gradient's going to be constant too. Now let's come up with our three equations. Our first equation is y equals lambda times 2. That's your fx. Your fy is going to be x equals lambda times 2. And then your constraint is 2x plus 2y is equal to 10. So these are your three equations. The three unknowns are x, y, and lambda. Oh, let me tell you that a lot of times we say that we solve for x, y, and lambda, but we don't really care what lambda is. And so a lot of times we're not going to even bother with lambda. We really just want to solve for x and y. But in the process, we may have to solve for lambda, and that's okay. Like in this case, I probably want to solve for lambda. So yeah, how would you want to solve for this? You have three equations and three unknowns, and it's just kind of like, go at it. Good luck. What? Huh? So substitute the lambdas. I have x is equal to something, y is equal to something, and then I just put that into the bottom equation. So I should have done this earlier, but let's factor out a 2, get rid of the 2, so I just have x plus y is equal to 5. So what do we have? X is equal to 2 lambda, y is equal to 2 lambda, and this is supposed to equal to 5. I have 4 lambda is equal to 5, and lambda is equal to 5/4. So again, I don't care about lambda. What I care about is finding x and y. So let's put that back into x and y. So y is equal to 5/4 times 2. That's the 5/2 that we got earlier. Y is equal to the same thing. Whoops. X. So we got the same result. We better have gotten the same result. But here we use Lagrange multipliers to get our result. Okay? How's that look? Is that right? All right, let's see if we can do something that's a little bit more challenging. Oh. Lost track of time again. Time flies when you're doing math. when you're kissing. All right, so we'll do a few more examples of this, and then we'll wrap up this section. I don't know if we'll introduce the next chapter tomorrow, but we'll see. All right, see you guys. Oh, quiz tomorrow at the beginning of class.